characters. And then Matthews has a nice paper who studies cheap talk in that setting. And then there are a few papers, like for example, Morton, that try to, and Cameron, that try to look at the dynamic setting where you have multiple rounds of such proposal making. And so the way how we contribute to this literature is by studying by giving the proposer the option to propose a menu, which allows us to identify first of an upper bound for the proposer's welfare that holds across all these game forms that they have looked at. And secondly, by solving this specific model. By doing that, we will see that there's actually a connection between this model and the literature on optimal expertise-based delegation. So let me briefly explain this expertise-based delegation. There you have a principal and an agent. There's a principal and an agent, and the principal has the power to make some decision, but which action he wants to take depends on some unknown state of the world. And then there's some expert that knows the state of the world. And then what this literature, starting with Holmstrom, looks at is how would the principal like to use the information of this expert. And in particular, they look at delegation mechanisms where the principal delegates the decision subject to some constraints to this expert. And then the expert actually decides. We show that there's a methodological connection or a deeper connection between these type of models, and the way we use we solve our model uses results that have been developed by Amador and Beckwell in this literature on expertise-based delegation. Conversely, the way we treat stochastic mechanisms, the method we developed for that could actually then also be transferred back to this literature on expertise-based delegation and might be useful if you're interested in working there to take a look at these results. There's a recent paper by Saran that studies a related question, and in particular, he has also presented in your seminar. So he also looks at the screening setting with single peak preferences. So our models are fairly similar, but then we go in different direction in terms of applications and the results that we actually get. So he reformulates the proposer's problem essentially as a dynamic programming problem. We try to characterize when specific mechanisms are optimal directly. So this is kind of the methodological connection to screening with single peak preference and expertise-based delegation, but the actual applications that we have in mind are more in the political science literature on proposal power and agenda setting. Are there any questions on the literature and before I move on to showing you the actual model?
I think there'll be more questions once you introduce the model.
Okay, so let's go there. Yeah, don't waste the time. So the model is simple on one slide. So there are two players that play the game, a proposer P and a veto player V, and they jointly determine an action, which is a number on the real line. The proposer has a concave utility function that depends only on the action that they take. And we assume that this is maximized somewhere, and you can normalize this maximizer to, for example, to be the action 1. So 1 is the first number you have to keep track of. This is what the proposer would like. This is his favorite policy. We assume that the utility function is twice continuously differentiable, except possibly at the peak. And for the veto player, we assume that he has a quadratic loss function. So his utility, if the action A is implemented and the peak of the agent is V, is minus V minus A squared. And importantly, the type of the veto player, V, is his private information. It's distributed according to some distribution F with a differentiable density F that has positive support on the unit interval. And the leading example that we have in mind or sometimes use is the assumption that the density is log concave. Now, this seems quite restrictive to assume here a quadratic loss function, maybe one comment in defense. For many of our results, actually only the ordinal preferences matter. Why? Well, once the proposer proposes a menu of options, the decision by the veto player is actually under certainty. So only his ordinal preference matter, and you could then replace this quadratic utility function by any symmetric loss function. The assumption of quadratic utilities does have bite when we study stochastic mechanism, because of the course, then even once you decide which potentially stochastic action to take, there's still uncertainty involved. So these are the preferences, and then the game is very simple. First, the proposer proposes a menu of options. So this is a closed subset of the real numbers. Then the veto player learns his type V and is going to choose an action A out of the set capital A, out of the menu that has been proposed. But the veto player always can use the action 0. So 0 is the status quo that's in place if the veto player vetoes all proposals that have been made.
And so where is the status quo in the preference?
So the status quo is just some policy, a real number, and then you can normalize it to be the number 0.
Oh, okay.
So if we implement policy A, this will be the utility, and if we keep the status quo, this just means A is equal to 0.
Okay.
So a stochastic mechanism would involve some probability distribution over A's, or will that be finite at that this thing? I mean, is there any loss in assuming that A is finite, or not, or no?
That A is finite?
Yeah. I mean, I mean, this isn't, particularly important, but I mean, is it important to have, to allow it to be a continuum or something like that? I was just wondering how you're then going to look at the stochastic version of all this. I mean, I'm going to offer different menus with different probabilities.
Okay, so the stochastic, yeah, so this is the deterministic version, and then the stochastic version that we look at is the agent is the proposer is offering a menu of lotteries with bounded support.
Okay, so it's a menu of lotteries. I see.
And then the agent, the veto player, picks a lottery,
okay.
And then only later on the outcome of the lottery is realized.
Okay.
Can I ask something?
Yes.
So yeah, so you were mentioning that in the previous literature, so your paper takes the approach that a proposer can propose the menu. So what was in the previous literature?
So the classic example would be where the proposer can just propose a single number.
Single number.
So the A would be a singleton, and then V either chooses this singleton or chooses the status quo 0. And yeah, and then there were these extensions where you allow first a cheap talk exchange where the veto player sends a message about his type, and then the proposer chooses a singleton, and then the veto player decides between the singleton and status quo.
So suppose if I think in terms of mechanism design approach that and say the direct mechanism. So the veto player announces its type. Based on type, I will just announce a single number. So how that thing is different from what previously studied, like the one you have just mentioned?
Okay, so exactly, very good question. So the mechanism design approach would say the proposer commits to a function that maps veto report to an action.
Right.
So, and this is essentially what we're doing, because by kind of a taxation or menu principle, you could replace this direct mechanism where instead of asking for a report and then implementing the corresponding action, of course, you can just let the vetoer choose among the range of this mechanism.
Absolutely, absolutely.
And so
I was just trying to understand that in the previous thing when they just announce a single number as compared, so how that is different from a mechanism design approach, because in that case also based on the report the proposer will just pick one number, right?
But I think the distinction is there is no mapping in the earlier problem. So there is
Oh,
some generality.
no commitment. Okay.
I mean, so the classic literature would correspond to one particular mechanism where that either for some subset of types you keep the status quo, and for the all remaining types you always implement the same action.
Okay.
And here we allow for a much larger class of mechanisms that give more discretion to the veto player.
Okay.
So what we're doing corresponds to the mechanism design approach, just because you're screening by providing a menu instead of using a direct mechanism. And the idea is that by doing this, you get an idea of an upper bound of the payoff for the proposer. And importantly, we are in line with this literature, we are not looking at transfers here. So this is all the models. So before I try to give some intuition into the economic trade-offs, are there any questions about the model? Any other?
No, just one question, that you allow the set of actions to be the whole of R. I mean, is there any technical reason why you do it, or would the result also work if it's a compact set or something?
So we will see soon that essentially only for deterministic mechanisms, at least only the actions between 0 and 1 will be relevant.
Okay.
I'll explain that. And if you had a discrete set of actions, the results that would get a little bit uglier to state.
Okay.
So just to come back to the benchmarks that we know. So the initial paper by Roma and Rosenthal was studying this as a complete information game where the proposer knows the type of the veto player. And then what the outcome will be that if the type of the veto player is below 0, this means the only options that are acceptable to the veto player are worse for the proposer than the status quo, and therefore the proposer will just offer the status quo. If the type would be between 0 and 1/2, then the best policy that's for the proposer that's still acceptable to the veto player would be 2 times V. Because at 2 times V, the utility of the veto player would be exactly as high as the status quo 0. And finally, if the type of the veto player was above 1/2, the proposer would always propose the policy 1, which is his favorite outcome. So in this case, we get that the outcome will always be Pareto efficient. Essentially, there will be no vetoes and P extracts all the surplus. And then in an extension, Roma and Rosenthal, in another paper, they were starting to look at the incomplete information game, where the proposer does not know this type V of the veto player and can propose just a singleton, which the veto player will then either accept or reject. And kind of the results that they get is it's not optimal to offer the policy 0. You mean you can always try to use your proposal to get something better, but vetoes will occur here with strictly positive probability. The outcome will in general be Pareto efficient, and there's a surplus sharing. So P extracts some surplus, but the veto player also gets some surplus due to the information rents. And now we're interested in how does this change if we allow for menus that are proposed instead of these singletons. And to come back to Debassy's question, so which actions could you propose? So any action outside of the unit interval is dominated, because if you propose an action above 1, and it's accepted, then you also could have just proposed the action 1 and it would also have been accepted. So really the issue is if the veto player wants something below 1, so it never helps to propose something above 1. And also it doesn't help to propose something below 0, because I mean, 0 is, if something below 0 is accepted, that's worse for the proposer than getting the status quo. That's why you can restrict attention really to the unit interval in terms of actions. And this holds even so, of course, the veto player might potentially find actions outside of the unit interval preferable. And now, given that you never want to offer anything outside of the unit interval, we call the menu, where you propose the unit interval, full delegation. I mean, this means that in our setting, you provide as much discretion in the setting as you could possibly expect. So given that you propose the full delegation menu, the unit interval, we will choose his preferred policy V whenever his type is within the unit interval. He will choose the outcome 0, the status quo, if his type is below 0, and the policy 1 if the type is above 1. So in this case, so if full delegation is optimal, we get a Pareto efficient outcome, and there are no vetoes. And what we find striking about full delegation being optimal is that essentially the veto player gets his first best. So whenever his type lies in the unit interval, he gets his first best policy, despite we give so much bargaining and commitment power to the proposer. In a sense, we give even more bargaining power to the proposer than in literature, and the literature typically has emphasized that there's a lot of proposal power for the proposer. We show that still the veto player is doing quite well here. So in the chat, there was one question. We are studying here the one-dimensional setting where types and actions are one-dimensional. So this assumption seems important in the sense that the problem is much more difficult if you had a multi-dimensional type and action space. So we don't have a good understanding of what's going to happen there, but we believe it is an interesting question to understand that area as well. Just as a starting point, we chose the one-dimensional setting. So it's unclear. It's definitely simplifying, and it's also substantive. We don't know how to solve the more general setting.
So just to clarify, so in case we take this to be unit square, then things are somewhat not readily generalizable, right? That's what you are saying. Yeah, it's not readily generalizable, and we don't know what will be optimal. Thanks.
So also, it's not clear that, I mean, are you going to provide conditions under which full delegation will be the optimal mechanism for the proposer? Or?
Sorry, can you say again?
So it's not clear that full delegation is optimal, right?
Yes, yeah. So I'm now going to discuss as a starting point when this will be optimal. Okay. Yeah, maybe I should. Yeah, sorry, let me explain this. So kind of to get an idea of what are the economic trade-offs, I'm now first going to explain when full delegation is optimal, then touch briefly upon no compromise, and then kind of the generalization would be interval delegation. So full delegation is one particular case. Let's see when this is optimal. To state the result, we need one piece of additional notation. Kappa is a measure of risk aversion for the proposer in a sense. Namely, kappa is the infimum of minus the second derivative of the proposer's utility function. Because this is concave, this is always a weakly positive number. Now, the first result is that full delegation is optimal if kappa times the CDF minus the marginal utility times the density is weakly increasing on the unit interval. So because the CDF is always increasing, in particular, we get that full delegation is optimal whenever the density does not increase too fast. So let's try to understand this result and go to explain a slightly simple lemma. So in particular, full delegation will always be optimal when the density is decreasing on the unit interval. So kind of why is that relevant? So a leading application would be where the density is unimodal. And then you could think about, okay, if the density is unimodal and the mode of the density is to the left of 0, then this means on the unit interval, the density will be decreasing. And therefore, full delegation will be optimal according to this corollary. And this implies in particular, if the mode is to the left of 0, this in the sense kind of you expect that there's a lot of misalignment of preferences. You expect, so we know that the peak of the proposer is 1. Now, if you expect that the mode, or if the mode of the proposer's most preferred policy is to the left of 0, so on the other side of the status quo, then there's a lot of disagreement about what is the best policy. But exactly in this case, you get that there's a lot of delegation, that there's full delegation. So this reverses, in some sense, the logic of expertise-based delegation, where the typical result is that if there is lots of misalignment in the preferences, then there will be less delegation, less discretion.
I have a small comment, or I am trying to understand that it is very similar to the chip talk game where delegation is optimal when the bias is very large, right? So here also when mode is towards the 0, the difference is very, or the alignment is weak, right? Is it true?
Yeah, when the mode is below 0, then there's little
not below 0. Yeah, sorry, towards 0. Away
exactly.
from 1.
Yes, the farther away from 1, the more misalignment.
So what was the support of V? I missed that.
So we assume that the support of V contains the unit interval, but it could be.
It could be 0 outside that, essentially.
So it could have support outside of the unit interval as well, or just on the unit interval. Yeah.
Okay.
So coming back to your, so the only difference is, so here we're measuring the kind of the disagreement in an ex ante sense, right? It's on where does the probability distribution put V, whereas in the delegation or cheap talk literature, the preference parameter, it's misaligned preference ex post. Even once we know the state of the world,
yes,
you can still vary. So that's a slight difference.
Thank you.
Just to clarify, this result holds for a weak concave function also, right? So suppose if I assume u of a is just minus a, then this proposition holds, right?
So we assume that u is maximized at 1.
Yeah, so I was thinking of minus of a minus 1 mod.
Yeah. So yes. Yeah. So you could think just a linear.
Yes.
Yeah.
Yes.
And another good question from the chat is the definition of kappa. What's about renormalizing this? Because it looks a lot like we're missing to divide by the marginal utility to get something like the arrow breadth measure of risk aversion. I think we could do that because the marginal utilities show up again in many other terms. So at least for the results that I showed today, you could define it with dividing it by the marginal utility, and then they would cancel out. So you could do that. I think the results look slightly nicer this way. So now I'm trying to give you the economic intuition for why it is that full delegation is optimal if the density is decreasing. Okay, so we do this in 2 pictures. So this picture shows on the horizontal axis the type of the veto player, and on the vertical axis we have the actions. So if you full delegation means that you offer the menu from 0 to 1. So all the blue actions are available to the veto player. So what does the veto player do? If his type is below 0, well, the best that he could choose is to choose the policy 0. If the type is between 0 and 1, he has the option to choose his favorite policy out of this menu. And if his type is above 1, then the best he can do is choose policy 1. And now we're wondering what's going to happen if you take out some actions. If you say you can't choose, for example, any action between L and H. So what is the induced action rule? So again, if the type of the veto player is between 0 and L, he can choose his most preferred policy. So he will get his first best outcome. And similar, if his type is between H and 1, he can choose his favorite outcome. Now, if his type is between L and H, his most preferred policy is not available anymore, and he has to make a decision between H and L, essentially. These are the two closest available actions in the menu that he can choose from. And the symmetry assumption implies that exactly at the midpoint, you have a jump. Any type that is below the midpoint will choose the lower action L. So any type in here will choose action L, and any type above the midpoint will choose the higher action H. Okay, so this is now two possible menus. If the blue menu is one option, you could give all the options available to the veto player. You will get the blue outcome function, or the red menu is a smaller one. You delete some actions, then you get the red outcome menu. And now we could plot in this graph, we are going to plot the distribution of the induced actions. So remember, F was the CDF of the types. But let's say the support is now 0, 1, and then the type is just the action, right? Because here we have the identity function. So then the blue is just the CDF of the action that's taken by the veto player if you provide the full menu from 0 to 1. And our assumption was that small f, the density was decreasing, so this will be a concave function. Now the question is, what is the probability distribution of the induced action if you provide the red menu instead? If you provide the red menu, this means that there are many types that choose the option L. There are many types that choose the option H, but no action in between will be chosen. So the probability distribution of the induced action will then be identical between 0 and L. And then there's a jump at L because a positive mass of types is going to choose this action L. Then it's constant between L and H because no one is allowed to choose an action between L and H. And then you have another jump at H. So what we show is that, and you can see graphically that whenever this density is decreasing, then F will dominate G in the second order stochastic dominance sense. And because we assume that the proposer has a concave utility function, this means that the proposer prefers to get this lottery F over the lottery G. So this is showing then that for the proposer, if the density is decreasing, it never pays to delete such a menu, so such an interval out between L and H, for example. And what's the reason? Well, there are two effects. First of all, you induce more variance kind of in the action because you force the veto player to decide between a very low or a very high action, whereas with full delegation, you would allow him just to choose something in between. So that adds risk for the proposer. And then decreasing density means just that there are fewer types are here. And these are the types where it would help to move from the blue policy to the red policy because the red policy is closer to the favorite outcome 1 for the proposer. And there are relatively more types here. And here it hurts to delete the actions because now you move away from 1 by going to the red policy. Okay. So there are two effects. In essence, you decrease the expected action that the veto player takes by deleting this interval, and you add more risk because you're risk averse. That's clearly worse for the proposer. It's kind of intuitively the reason why you want to give many options to, you're willing to compromise a lot if you have a decreasing density. On the other hand, if the density was increasing on this interval from L to H, we would get that deleting this interval increases the expected action, but also adds variance. And it turns out that this is desirable whenever the ratio of the derivative of the density divided by the density is large compared to the Arrowbread measure of risk aversion. With linear utilities, you get that this last term is 0, and a decreasing density is necessary for the optimality of full delegation.
So if the CDF is convex, then what did you say? What happens? It's not clear, is it?
If the CDF, it's not clear if the utility function of the proposer is strictly concave in the relevant region.
Right.
But if it were linear, then you would get
Sure.
that full delegation definitely is not optimal. And one question, so can we think of this as a mean preserving spread? I mean, almost like we think it more like in second order stochastic dominance, because F and G don't necessarily have the same mean. Because here this jump is larger than this here because F is concave. But yeah, second order stochastic dominance, yes. So this is the basic economic trade-off that you face. So by giving fewer options to the veto player, you increase the risk for the proposer, and then whether it helps the expected action depends on the shape of the CDF in that region, whether it's more like concave or convex. And so our first result was whenever the CDF is concave, then full delegation will definitely be optimal. So this would be one extreme where there's a lot of discretion for the veto player. The other extreme is no compromise, where well the proposer always wants to propose one because this is his favorite policy. You can never hurts to propose it. If it's chosen, it's good, and if not, well, it didn't hurt at least to offer it. So if you're just going to offer your favorite policy one, we call this no compromise. You're not willing to provide anything in between the status quo and your most preferred policy. So we show that, or it follows fairly easily that whenever the utility function is differentiable at 1, then no compromise is not optimal. Why? Well, because the utility function is maximized at 1. If it's differentiable at 1, this means that the marginal utility at 1 is equal to 0. And then by offering some compromises close to 1, you get only a second order loss if these are chosen instead of 1, but you can reduce in a first order sense the probability of a veto outcome. That's why if you have a differentiable utility function, you always want to offer some compromise policies around your peak. On the other hand, you could assume that what we had before, that the utility function is a linear loss function. And if the density is increasing, then no compromise is optimal. And this follows by a similar logic from what we had before. But it turns out that this condition is much, much stronger than what's needed for no compromise to be optimal. So this increasing density, we show that in a sense, you just need that the CDF is in a sense convex on average on the interval from 0 to 1 for no compromise to be optimal. With linear U, this means that the density at 1/2 is a subgradient of the CDF at 1/2. So this is would be the opposite extreme where you're not willing to compromise at all. And to state the general result, we introduce interval delegation. We say that the proposer engages in interval delegation.
One more question on the singleton thing once more. So instead of, I mean, is it without loss of generality that amongst the set of degenerate menus, you only consider 0, 1, but you could also potentially consider 0, Q, where Q is some point between 0 and 1 also. is that going to improve the outcome for the proposer potentially?
Yeah, very good point. So among the singletons, it's without loss to just look at this policy 1. And the reasoning is the following. So instead of proposing just some policy Q that's between 0 and 1, you can offer the menu Q and 1. And I mean, all that can happen is either the veto player chooses Q as before, but sometimes maybe now he's taking policy 1, but this is the best for you. So this always.
But I want to only look at the menus which contain 0 and one more outcome.
Okay. Sorry, now I understand. So this would be essentially what the Roma and Rosenthal or the literature building on that did, right? Where you can just propose a single policy.
But they also have incomplete information. So
the original paper didn't have incomplete information, but there's follow-up work that had incomplete information, and then solve for what is the optimal singleton that you want to propose. And I have a comparative statics result later on comparing these two.
Okay.
So just a related point, say for example, the Q is expected value of that, then what will happen?
Sorry, so Q is
this Q, the second point what Debashish was proposing, that this Q is suppose the expected value of this F of this 0 to 1, that distribution, that the veto player's distribution, the expected value of that. So what will happen in that case?
So if the proposer is proposing the expected value of V,
so 0 and Q, yes, the degenerate menu, it is 0 and the expected value.
I don't have a good answer. I mean, sometimes this could be optimal, but in general, this is not necessarily the optimal singleton that you can propose. So the basic trade-off that you face by choosing a higher singleton, you increase the probability that there's a veto, that the veto player chooses 0, but conditional on acceptance of this policy, you get a higher utility, but it's not necessarily at the expected value where it's maximized.
A clarification. So you have shown that in this, no compromise is not optimal when this condition holds, irrespective of the distribution of V, right?
Yes. I mean, just assuming that the support of the distribution contains the unit interval.
Yes. Then like, okay.
Okay, to state the more general results, so we introduce interval delegation. We say the proposer does interval delegation if he proposes some interval from C up to 1. Okay. So it's clear because the proposer always wants to include 1 as a policy in his menu. So if the menu is an interval is optimal, then it will be an interval of this form C up to 1. And then the veto player always has the option to choose policy 0. So in special cases, this subsumes the interval delegation where C would be a full delegation where C would be equal to 0, or no compromise where C would be equal to 1. So in general, we get that if C is strictly positive, then we have vetoes and Pareto inefficient outcomes. And interval delegation seems particularly simple to analyze, for example, for comparative statics. And at least in the delegation literature, people argue that it seems more relevant for application because it's much simpler to implement, practically speaking. So now we're interested in when is it optimal to offer an interval, and what is the optimal interval. So the first result is kind of just a simple sufficient condition when interval delegation is optimal. So whenever the proposer's utility is a convex combination between a linear loss function and a quadratic loss function, and the density is log concave, then interval delegation is optimal. And why is that? Well, very roughly, if the density is log concave, this means it's in particular, it's unimodal. So it's single peaked. It's increasing up to a point and then decreasing. And we've already seen before that on the decreasing part, it's optimal to provide lots of options for the veto player. And on the increasing part, you want to provide little discretion. And it turns out that for this combination of utility function and imposing log concavity, which implies this unimodality, you get exactly that interval delegation is optimal. In the paper, we have a precise characterization when interval delegation is optimal, but it's not that nice. And I wanted to put the emphasis on a few other things here. So just one takeaway is quite often under relatively nice conditions, interval delegation will be optimal. And then the question is, if interval delegation is optimal, what is the optimal threshold that you're going to use, this C? So let C star be the optimal interval threshold. This means that you're going to offer the menu from C star up to 1. So in general, multiple maximizers could be possible because the proposer utility might not be quasi-concave, but then our comparative statics results go through. I just take the simpler version, assuming that this is unique. So suppose that P star is the optimal singleton proposal. So this is what the buses had in mind. If you can just propose a singleton in addition to the zero policy. So suppose then that P star is optimal. So we get that the optimal menu, if you propose an interval, will always have a C star below P star. This means you're more willing to compromise than in the singleton case. So the reason for this is fairly simple, because if you just can propose one singleton, the P star, then you're wary to put it too low, because even very high types of the veto player that have essentially the same preference as you have will choose this P star. And therefore it's painful to put it too low. But if you can propose a menu, of course, then the high types of the veto player, they can still choose a policy close to 1 if they want. And only very low types will choose the menu with a point C star. So it's not that painful to choose it lower. And that's why it's optimal to put it always less than P star. This also implies that whenever a menu is optimal, we will have a Pareto improvement over the singleton case. Clearly, the proposer likes it to have the option to propose menus instead of singleton. And under this condition, the veto player also prefers being in a world where menus are possible. So that's why it's a Pareto improvement compared to the singleton case. The second, making more precise the idea that we had before, if the density increases in the likelihood ratio sense, in particular, we interpret this as that in expectation, the preferences become more aligned because the most preferred policy of the veto player moves closer to the policy 1, then the C star, sorry, this would be C star, increases. So this means that whenever the expected most preferences of the veto player move closer to the preferences of the proposer, then the proposer is actually willing to delegate to provide less discretion. And this is kind of the opposite result that you get in the expert-based delegation, where you have, if they are more aligned, you provide more more discretion. And finally, a very natural result, if the proposer becomes more risk averse, then he's more willing to provide discretion because kind of he's afraid of the veto outcome. Even so, this is a very natural result. It turns out that all these results only hold when intervals are optimal. And if you have other kinds of optimal menus, then all these comparative statistics results can break down.
The tradition for me and other gamers, like every gamer, do not get recruited. If you get recruited, you're going to get bad luck.
Excuse me, can you mute yourself?
And with recruit song, so I am not here.
Yeah.
Okay.
Sorry.
Thank you. So I gave you the main intuition for why this kind of results hold, and now I want to at least briefly touch upon the methodological part where we formulate the problem. So for any menu that you provide as options to the veto player, this induces a choice function alpha. namely the choice function that you get that the veto player of type V chooses his most preferred policy out in the set A and 0. So it turns out that instead of optimizing over these menus, it's easier to optimize over these choice rules, or essentially these are just direct mechanisms without transfers. So let D be the set of all those functions, let's say mappings from the unit interval to the unit interval that assign the policy 0 to the type 0 and that are increasing. But these are two necessary. This is the IR constraint, because we know that the type of 0 has the most preferred policy 0, but policy 0 is just a status quo that's always available. So clearly every mechanism that's available has to assign policy 0 to the type 0. And incentive compatibility implies that this alpha function has to be increasing just because it's a single crossing world. So then one could state with deterministic mechanisms, one can state the proposer's problem as he's choosing a mechanism in this set to maximize his expected utility, where expectation is taken over the type of the veto player. And to get incentive compatibility, we have an additional envelope constraint. So this is essentially the problem that you're looking at with deterministic mechanism. It turns out that this is not too nice because the constraint set that you have here is not a convex set. If you take a convex combination of two incentive compatible mechanisms, this will not be incentive compatible here because we don't have transfers and we have these nonlinear utilities. So we were looking for other ways to solve this, and we found a nice way to solve this that even allows us to take care of stochastic mechanisms. So let me also briefly state the problem with stochastic mechanisms. So let this L denote all the CDFs that have a bounded support. And then as a set of stochastic mechanisms, you can look at all those mappings that map the type, so the unit interval, into such a lottery. Now, again, we have an IR constraint, namely the type 0 should get a lottery that puts probability 1 on the policy 0, because this is exactly his outside option. And we want that the expected value of this sigma function must be weakly increasing. This is implied by incentive compatibility. And then the problem of the proposer is now again to choose, in this case, a stochastic mechanism to maximize his expected utility. The expectation now is again over the type of the veto player, but also about the outcome of this lottery. And we have again an envelope condition that ensures that the mechanism is incentive compatible. And so what we get is that instead, so this is the problem that we're really interested in. And it turns out that there's a simple relaxation of the deterministic problem that allows us to solve the stochastic problem in one go. And what we do is we essentially replace this equality constraint by an inequality constraint, so that the left-hand side is weakly greater than the right-hand side. And then we solve this relaxed problem using the Lagrangian techniques that have been developed by Amador and Beckwell. And then we have two results that show that if the solution to this problem is incentive compatible, then it must actually also solve the stochastic problem. And conversely, whenever you have that the deterministic mechanism solves the stochastic problem, then it must solve this relaxed problem. And the relaxed problem, because this becomes an inequality constraint, now it's a nice problem that has a concave objective functional and a convex constraint set, and yet you can use the nice techniques to get necessary and sufficient conditions for a particular mechanism to be optimal. So this is kind of the basic idea that seems to generalize also to the expertise-based delegation and give stronger results there as well.
Can I ask a very stupid doubt? So in the deterministic version, the IC condition you have written, is it equivalent to the standard IC that the the voter cannot gain by lying some other type, right? So that is the IC.
Yes, so IC comes from you cannot misrepresent as another
Yes.
type exactly. And then usually you have, for example, in Meyerson and all these things, you have the nice characterization of incentive compatibility via a monotonicity condition that the allocation is increasing. This is the part here. And then you have an overload condition that in Meyerson would fix the transfers, right? So once you fix the transfer of the lowest type, it tells you transfer. So here we don't have transfers. That's why just by choosing this allocation alpha, you already must satisfy this envelope condition.
Okay.
And the envelope condition looks slightly different because we have nonlinear utilities. That's why this is a nonlinear function here. But yeah, you're perfectly right. This is the idea. So that time management, I'll skip the application and talk instead briefly about the role of commitment that we are assuming here. So in the model that I just showed you, we gave the proposer all the bargaining and the commitment power, okay, by taking this mechanism design approach. For example, we saw that often it's optimal for the proposer to propose some interval C up to 1 where C is strictly positive. And then the outcome will be that either the veto player chooses one of these options, but often he will also veto all of them, and then the status quo obtains. So in this case, the proposer would commit not to come back to the bargaining table and make an additional offer, right? So this, in a sense, that commitment power seems important there. And we were a little bit concerned or interested in how important this assumption is and how, yeah, what is the role of commitment here? And to analyze this question in an ongoing work, we study instead.
You know, one question, you're also assuming that the vetoer cannot, you know, has no commitment powers as well. So for instance, in the example that you showed earlier with the diagram where the vetoer, you know, the thing where the vetoer cannot choose anything in the middle interval, right? So the vetoer could say, okay, if you give me that, I will reject everything, or I will randomize equally between the two ends of the interval or something like that, right? And force the proposer to propose something else. Is that important in some way?
I think it's important, right? I think you're right. Otherwise, you could think of a strategy where the veto player says, if you're not giving me full discretion, I'm always going to pick, let's say, the status quo. This is what you have in mind, right? Yeah.
For instance, or randomize in some way, or even do other crazy things.
Yes, yes, you're right. So that's clearly important. Kind of the motivation for doing that is in line that we are interested to give all the bargaining power to the proposer and see how good can he be, how high can his payoff be. Now you could think of many other game forms where the outcome will closer to what you have in mind if you give more bargaining power to the veto player. So for now, we were just interested in this part, and I agree, other game forms give very different outcomes. But in this part now, we're trying to understand the role of the commitment power that we gave to the proposer. And so to do this, we study a dynamic bargaining game where in each period, the proposer can propose a single policy. Now it's just a singleton. And then the veto player is going to either accept it or reject it. And if it accepts it, the game ends. But if it rejects it, we move on to the next period, and then the proposer can make another proposal. So it seems like an interesting and relevant model of this kind of such dynamic bargaining situation in itself. And indeed, there's a literature that has been working on that. So Roma and Rosenthal studied a simplified version of this, where the veto player is not forward-looking. Or Morton and Cameron look at two-period versions of this game. And also Rosenthal and Same have a recent paper that look at the two-period game. So in general, this is a difficult game to study. But it turns out that with the insights that we get from the mechanism design approach, it gets a bit simpler to find equilibria here. So we illustrate in this part how our first project can be used to study related bargaining models, and it allows us to analyze the commitment issue the commitment power that we gave to the proposer in the first model. And this is a little bit analogous to what we do in a monopoly setting when we look at the Coase conjecture. So suppose you look at a price discriminating monopolist who has one object to sell, durable good. So we know that the optimal mechanism is just to post a price, and then this maximizes the revenue of the monopolist, and then the buyer can decide whether he buys at this price or whether he's not going to buy. But we assume typically that the monopolist is not going back to the buyer and makes him a lower offer after rejection. So to study the role of bargaining there, Coase has proposed a model where you look at this as a dynamic game, and in each period, the monopolist proposes a price. And if the buyer rejects the price, then in the next period, the proposer can again propose a different price. And he conjectured that this change of the commitment assumption will lead to a stark decrease in the revenue for the monopolist. And the results that we find in the literature is mainly in line with his conjectures. So in every perfect Bayesian equilibrium, the proposer will propose a decreasing sequence of prices. Even so, the commitment solution is to have a constant price. Higher types will buy earlier. And we get that as the agents become patient, already the initial price that the monopolist charges will converge to the lowest valuation of the buyer whenever this is strictly positive. So in a sense, by relaxing the commitment assumption in this world, you get a huge drop in the expected revenue for the monopolist. So initially, when we started this project, we were expecting something similar to happen in our world. And it turns out that this is not true because preferences are rich in our model. So I know I don't have much time left, but let me just briefly mention the main insight that we get from this. So the model is as before. So the two players, proposer and veto player, determine jointly in action A. Now time is discrete with an infinite horizon, and the players get flow payoffs. Initially, the status quo is in place until they agree to some other policy. And if they agree to some other policy, then this other policy will remain in place forever. And in each period, they get the flow payoffs and discount them with a common discount factor of delta. And again, we're assuming that the type of the veto player is private information and that it's constant over time. And now the game is a dynamic game. In each period, if all previous proposals have been rejected or vetoed, the proposer can propose a new action or policy a singleton, and the veto player can either accept this action, in which case the game ends and we implement this action forever, or the veto player vetoes this action, the status quo remains in place, and we move on to the next period with another proposal. It seems like this is the natural analog of the Coase conjecture world, where you study a dynamic game instead of looking at the mechanism design solution. So what's going on in this world? So to give you the key idea, let's look at the simple version where you have just two types of the veto player, low type and the high type. Let's say, again, everything is between 0 and 1. So 1 is the policy that the proposer likes the most. 0 is the status quo. Let's say the low type is below 1/2 and the high type is above 1/2. And the high type is more likely. And the proposer has a linear loss preferences. So to give you a couple of benchmarks, so the first best outcome, of course, for the proposer would be to get policy 1 if the type is high, and to get the highest possible action subject to IR if the type is low. This would be these two actions. Now the basic problem is if you have private information, the high type would like to mimic the low type, because clearly the high type, his favorite policy is this V upper bar. So he definitely prefers by mimicking the low type. So once you take this incentive constraint into account, then the commitment solution would be to say, okay, if you're a high type, I propose the policy 1 to you and you accept it. But if you're the low type, I propose you a policy that makes the high type indifferent between accepting the policy 1 and choosing this lower policy. So if the proposer could commit to a dynamic strategy in this game, he would commit to proposing first the policy 1, and if it gets rejected, then he would propose policy close to this A lower bar C. And then the high type of the veto player would be willing to accept the first proposal, and the low type would be willing to accept the second proposal. The problem is such a strategy is not sequentially rational, and this is like in the Coase world, because the high type realizes that if he, after rejection in the first period, the proposer knows the veto player is a low type, and then he would want to propose 2 times V lower bar, because this is the highest policy that's still acceptable to the low type. But if the high type anticipates that the proposer will propose this higher policy, then he doesn't want to accept this policy 1 in the first place. So this policy is not sequentially rational, but it turns out that because preferences are here so rich, the proposer has more strategies available. And in particular, what the proposer could do is to first propose a policy that's close to A lower bar C, slightly below. And if it gets rejected, then he's going to propose policy 1. Now what's going to happen in that case? The low type will accept this lower proposal because it's fairly close to his most preferred policy, definitely better than 1 and better than 0. But then once it's rejected, the proposer can update his belief and learn that actually the veto player is a high type. And then he will propose policy 1 to the high type because he knows 1 is better than the status quo for the high type, so the high type will accept it. So by targeting the low types first, you can actually relax the sequential rationality constraint in future periods. And it turns out that this is a tremendous help to overcome this issue of limited commitment. And so I'll just end with this result. In the general model, we find that for suppose that an interval is the optimal solution in the static problem that we've been looking at that gives the proposer an expected payoff of U. What we find is that for every epsilon, whenever the discount factor is high enough, there exists a perfect Bayesian equilibrium that gives the proposer expected utility of at least U minus epsilon. So in a sense, this version of limited commitment has virtually no effect in this equilibrium on the payoff of the proposer. This is in stark contrast to the Coase world, where you get that this effect of limited commitment is very stark and leads to very small payoff to the monopolist. Here, the proposer still gets very high utility. And the reason why you can do this is because here the preferences, we have the spatial single peak preference of the veto player. This allows you to first target very low types. And this is very helpful because it helps you to relax the sequential rationality constraint in future periods. And from a methodological point of view, so this problem has a very rich state space, and it's in general, we find it very hard to construct equilibria here. But having this upper bound that we get from our static solution helps us in actually showing that at least there exists a sequence of equilibria that gives you in the limit the same payoff. So this also, on the one hand, this illustrates how we can use the mechanism design solution to study related problems, for example, of dynamic bargaining. And on the other hand, this dynamic bargaining problem also shows that this commitment assumption has less of an effect than, for example, in the world of a durable good monopolist. So just a quick wrap up. So the first part of the project, we took a commitment or delegation approach to a veto bargaining problem, and we found a new rationale for delegation. The proposer is willing to offer a menu of options to the veto player because he's unsure of what's acceptable to the veto player. We find that typically non-singleton menus are optimal, and that often the veto player obtains very large information rents. For example, full delegation can be optimal, even so we give lots of bargaining and commitment power to the proposal. And then I've briefly touched up on our dynamic model, where we look at the dynamic bargaining game, and where we show that even with this relaxed commitment assumption, the proposers still can achieve the same payoffs in the limit where agents get patient. I know this very last part was probably too much. I just wanted to give you an idea of how one can try to use the results from the mechanism design solution to actually study related models like dynamic bargaining. So are there any questions?
If
Can I ask
there is a question, please go ahead.
clarificatory question? So could you just go back to the slide where you have just two types, V lower bar? Yes, in this slide. So in this slide, sorry, I didn't follow that. Why first proposing a upper bar and then a lower bar is not sequentially rational? Because you said that V upper bar is indifferent between a lower bar and a upper bar, right?
Exactly. So yeah.
So then why would he reject when the say V upper bar reject a upper bar in the first period?
So the issue is the following. So suppose you look at the strategy profile where you first propose one, and upon rejection of one, you believe that the low type is now with probability 1, because you know the high type, he was indifferent, or he should have accepted policy 1. But now if you're absolutely sure that it's the low type, for the low type, you don't want to propose the policy a lower bar, C. Instead, you want to propose the policy 2 times V lower bar. Sorry, the one that we had here, because this is the policy that makes the low type indifferent between status quo and the policy that you propose. So kind of you want to commit to make a low proposal after rejection.
Thank you.
You made a remark that the reason why the Coase conjecture was not working here was because of the richness of preferences. By that you mean single peakedness, that I can go in both directions or something? Is that what you mean?
Yes, exactly. So in the Coase world, the analog of such a strategy would first you propose a very low price. But of course, for a durable good monopolist, then all the buyers want to buy at a low price, because they kind of all have the same ordinal preference. They all always prefer lower price over higher price. But here the spatial preference imply that higher types actually prefer higher policies over lower ones. So it's not clearly ranked.
So that's it seems to be an important observation even in the Coase world, isn't it? I mean, you can think of more, can one think of more general preferences where the Coase conjecture is completely overturned? Is that what you were suggesting? Different kinds of preferences. I don't know what. With characteristics or something like that, or something. I don't know. I'm just saying something, but it just seems somehow important.
I think this is an interesting point to think about the standard monopolist setting. If you have somehow richer product space and richer preferences, to see which part remains of the Coase conjecture and which part is more like here. Yeah. I haven't thought about this much, but it's an interesting point.
So there is a question in the chat box. Do you want to answer that?
Yes. Maybe you can elaborate. So the idea is now, if the veto player does not know perfectly his preferences, maybe there's some other unobserved state of the world that affects his preferences, and then the proposal could now in addition provide information about that state. That should give him more control. I agree. I don't have much else to say. Yeah, if the proposer can commit to a choice of a signal structure, I mean, that seems like a good world for the proposer.
Yeah.
But I don't have a good idea of how the optimal mechanism would look like or how tractable it is.
So I think this is a very interesting class of problems you have studied. I was not aware of this class of problems. But let me ask, there's this recent literature in computer science about providing bounds on with simple mechanisms. What can you do? So I was thinking like, for instance, the Amador, no, not the Amador, Rosenthal paper, the first Rosenthal paper, which determines the, you call it Q star or something, the with singleton menus, what the optimal is. I mean, I was thinking like, how bad can it be with respect to the, let's say, the full delegation mechanism or whatever the optimal mechanism you found out. I mean, have you thought about it? Like how bad can it be? I mean, can you provide a bound on the loss of utility for the proposer if he restricts attention to this simple mechanisms in the class of that Rosenthal mechanisms? I mean, that seems like a natural question because here it's very difficult to describe the optimal mechanism per se. You provide conditions under which full delegation is optimal, and then these interval delegation is optimal. But inside the interval class, it's difficult to pin down exactly which interval is optimal. So maybe, picking one candidate mechanism and showing that it can pretty much recover what the optimal would be could be an interesting question also, right?
Yes, I agree. So I think finding the optimal interval is not that difficult, but I agree that the overall problem still is finding this sufficient condition and so on is difficult. And it's definitely interesting to know what simple mechanisms, how good they're doing. I don't have much to say there. I mean, so here there's always a big risk that there is a veto, which is kind of the worst possible outcome. So the question is, how can you put a bound on the probability of a veto, essentially, depending on what information you or kind of what you're minimizing over.
Also, there is this literature on robustness, right? So basically, there is a certain uncertainty about the distribution of types and so on. So, and would that also result in a simpler mechanism to be optimal if you add this layer of robustness and so on? All these questions, I'm just conjecturing them to be interesting questions. I don't know how tractable they are and so on.
Yeah. Yeah, robustness seems like a good idea. I mean, this could push one in favor of a full delegation, I guess, but it's, I think seeing the effects of, if you want robustness, what this does to your optimal mechanism, it seems interesting. I agree.
Any other questions? Okay. Thank you, Andreas, again. Thank you for your talk.
Thank you for inviting me.
Please stay on. We'll chat a little more.